Now this is a standard enough complex numbers question here, okay, so as usual it's a 25 marker, which complex numbers tend to be, but what's interesting about this one is they have simultaneous equations in it. Like most good Leaving Cert questions, the best ones are the ones where students may never have seen anything like this before. Okay, so it hasn't really come up in any other Leaving Cert. I haven't seen it in any books or anything like this, but then you're just thinking back to what do I know about complex numbers, what do I know about simultaneous equations, and away you go. Now first of all here, let's just look at IZ1 is equal to this. Okay, now IZ1 is being equal to that isn't much good to us. However, if we get Z1 on its own, okay, then we can use that down here then and substitute that in there. So that's our first step here, is to get get rid of this I, and there we go. Now this should be ringing a few alarm bells to you there, because you cannot have a complex number underneath the line. Okay, so it's one of the fundamental rules of complex numbers, and to solve that, there should be a well-prepared student will have no problem with this. To get rid of a complex number underneath the line, we're just going to multiply above on the line by I. Now, you could do by minus I as well, but in this case, I is fine, right? As long as you do the exact same thing above and below the line, when you multiply that out, the I squared becomes a minus 1. That gets rid of the complex number underneath the line. Just be careful with your signs here, right? So that stays the same. That goes to minus 3. And to get rid of the minus 1 underneath the line, you just change everything to a positive. So plus 3 plus 4i, and just put the real one first, complex one second. So now we have a value for Z1, and like all simultaneous equations, you then take your value that you know from the first equation and substitute it into the second equation. So Z2, and in this case now, in hindsight, I actually didn't need to do this, as you'll see in a second, right? But usually with identities, you just call Z2 A plus BI. Okay, so we're going to substitute 3 plus 4i in instead of Z1, A plus BI in instead of Z2, and we get this equation here. And it's just an identities question then after that, right? So we just multiply out our brackets like this, I'm just going to get the A's and B's on the left hand side and everything else on the right hand side, and it'll look like that. And that's actually our answer then. Okay, I didn't actually need to put in the A plus BI. I could have just left it at Z2, and it comes out as 2 minus 5i. Now, part B then is quite interesting. So we had simultaneous equations in the first part, and now here we have a geometric sequence. So that's one thing they do with complex numbers quite often, is they mix it up with different topics, like sequences and series in this case. So as soon as you see geometric sequence, you're thinking, right, well, for a geometric sequence, what do I know about them? Well, I know that if I have 3 terms, then the common ratio is the first term, or one term divided by the term before it. Okay, so I can divide that by that, but I can also divide that by that. So here they say these complex numbers are the first 2 terms of a geometric sequence. Right? So to get the common ratio, I'm dividing one term by the term before it. Okay. Now that comes to our second rule then. What happens when we divide in complex numbers? And we kind of touched on it in part A, but to get rid of we can't have a complex number underneath the line, so we're going to multiply above and below by the conjugate in this case. Okay, so by combining these 2 rules, to get the common ratio, I divide the second term by the first term, which is that, and to now our complex number rules, to get rid of the number underneath the line, we're going to multiply both by 3 minus 2i. Now look, this is the way I do this. Whatever you want to, the next step, whatever you want to do it, just be careful with it. But what I usually do is just take the top line over here separately and multiply all those brackets out. Watch out for the I squared, change that to a minus 1. Watch all your signs. And then take the bottom line and do the same over here. And again, whatever way you do it, it's fine. Just take your time, make sure you don't make any mistakes. And even without checking the solution, I have a kind of a good idea that I'm probably right in this case, because all the 13s, when I put them back in together like that, the 13s will all cancel and I'm left with 1 minus I. Okay, so the common ratio of this geometric sequence is 1 minus I. This is where it gets interesting. So there's my solution from the previous section. So use the Moivre's theorem to find T9, the 9th term of this sequence. Okay, now so where are we going with this? Right, and again, this is another one like part A, where students would never have seen this in a complex number question before this, right? But all the individual parts should be straightforward enough, because with geometric sequences, well, I know the formula is this. Okay, so where A is your first term, R is your common ratio, and we know those 2 values. We know the first term is 3 plus 2i. We know the common ratio is 1 minus I. So let's just see where we can go with this. And we're just going to substitute these values into the geometric sequence formula, and we get this. But where does the Moivre's theorem come into it then? Okay, well, as you know well now, the de Moivre's theorem is a kind of a shortcut to getting a power of a complex number. But to use de Moivre's theorem, we need to get it in polar form first of all. And just in this case, R is the modulus, right? That's your formula for the modulus. That should be all, routine for everybody. There should be no problem with this. But where does it fit in here? And straight away you should be able to see that, well, I need to get 1 minus I to the power of 8. So that's where you're going to use your de Moivre's theorem. Okay, so first of all, we need to get 1 minus I in polar form. Very routine thing. So you're first of all, what I always do is draw out a rough diagram of the complex number on the Argand diagram. My modulus is that distance there, and my argument is that angle there. Okay, so modulus straightforward into this formula, and it comes out as root 2. Now the argument then is slightly more challenging to find, but someone, I know I keep saying it, but a well-prepared student will see that, right, well, if I'm going out 1 and down 1, then that angle there has to be 45. Okay, so therefore that angle there must be 315. Now, if you want to go the long way about doing that, drawing out your triangle with a side one, an opposite one, and an adjacent one, and work out your angle there, that's fine. But the more experience you get with these, you'll spot straight away that that's a 45-degree angle in there. So therefore my argument is 315. 360 take 45 is 315. So there's my number there's 1 minus I in polar form. So then to use de Moivre's theorem, then we want this to the power of 8. And you just use your de Moivre's theorem there. So the root 2 goes to the power of 8. We multiply our angle by 8 each time. And it looks quite complicated. But when you multiply it out, that to the power of 8 is 16. Cos by 8 of 3 by 315 comes out as 1. And this comes out as 0. So 16 by 1 plus 0i is just 16. And you should almost always, it's not a hard and fast rule, but nearly always it simplifies down to something simple like this. So all of what were we looking for at the very start? We were looking for t of 9. So all of this simplifies down to just 16. So to find t of 9, it's just 3 plus 2i by 16. So, which is that, multiply it out. And so that what that says is in this geometric sequence of complex numbers, the 9th term is 48 plus 32i.